All right, now I'd like to talk about graphs of these kinds of distributions. Now, when I say graph, I mean, for example, flipping a coin. Coin 5 times. Actually, no, I'm not going to do it 5 times. I'm going to do it 10 times. Okay, so the number of successes are, and the probability that x equals this, we're going to set up a little table of values. So we're doing it 10 times, so I want to find out the number of the probability of having 0 successes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 successes. Why would I have even gone all the way across to there? So, what's the probability if I toss it 10 times that I only have 1 success? Well, Px equals 0 successes is, well, and it is going to be 10. Probability of success is a half. So I've got 10C0 times a half to the 0. So that's the number of successes I got. Half to the 10, which is the number of failures I got. This is just going to come out as 1 over 1024 because 10C0 is 1. Probability x equals 1. 10C1 times a half to the 1 times a half to the 9. This is going to be 10 on 1024. I know the bottom's 1024 because I know 2 to the 10 is 1024. Okay, if I have any x equals 2, that's going to be 10C2. And we'd keep going. All in all, if I were then to graph this, and this top one, the y-axis was the actual probabilities that it came out as that. And this is the number of successes I wanted. And I had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, why do I go for such long x-axes? If you'd actually put the numbers in, and I'm not going to put those numbers in because I don't have a calculator with me. Our graph, oh, and this was like 0.05, 0.1, 0.15, etc. Our graph would have ended up looking something like, these are so close to 0. And then we start kind of going almost up. And then we'd kind of I think I should have had a much smaller thing. And I'm trying to find one that's already been drawn in the textbook. Anyway, we would have ended up with something that looked like, that was terrible. We would have ended up with something that went like that. I'm going to ignore these numbers because I can't be bothered to chuck it in my calculator. So then we would have chucked a line through them and it would have come out like this. And so that's a graph of the distribution, and this is what we call non-skewed because it's symmetrical. But you can have others, and I'd like to take us to, really? Oh, it's the extension, Year 11 extension textbook. Anyway, I'd like to take us to one they've already done because, again, crunching these numbers is painful. Z scores what's that? 16, okay. Come on. Okay, almost there. Oh, come on. Sorry about, oh my gosh. Sorry, guys. This is really annoying. So all we've done is graphed the probabilities. And here are some examples. So with this one here, this is the one we just did. And you can see that it takes a shape roughly like that. This one's been done 20 times, not just 10 times. Oh. Now that's rolling a dice. That's flipping a coin, sorry. This second one is rolling a dice, and when they crunched the numbers, it looked more like this. So it started high and then went down low. And this is what we call skew to the right. Which is positive. Just want to put this picture in. So this is what it looks like when it's skewed to the right. And then you can probably guess what it's going to look like otherwise. Oh, come on. Yes, skewed to the left, and it's called negative. But each time they've crunched the numbers and they've figured out the probabilities for each thing, and they've ended up with a graph that looks like this. That's it. That's the last kind of thing you needed to know for these. Oh, one useful thing to know, not necessarily like you have to, but one useful thing to know is that p equals half, you're going to get symmetrical. When p is less than a half, you're going to get skewed to the right, which is positive. And when p is greater than a half, you get skewed to the left, which is negative. Okay, that's it.